This series was made to describe an alternative interpretation of physics, one where the universe is local and real and has an infinite scale, where space-time is real and everything is fundamentally just motion. I spent the previous videos arguing against some of the most common criticisms levied against this kind of idea. Now I will actually describe what this interpretation is and how it could work. While I personally like this model, I must admit that it's nothing more than pure speculation, and that it should be listened to with a heavy dose of skepticism. The standard model of physics, as described by quantum mechanics and general relativity, is already a very accurate description of reality, and is most likely true. I'm just trying to argue that this type of local and real interpretation may be plausible, in that it hasn't been entirely ruled out yet and may be consistent with most, if not all, currently available evidence and observations. This doesn't make it true in any way, but it should make it worth discussing. And I personally believe that it would be beneficial to discuss this kind of interpretation, because I think that the models for a local and real particle that are currently being used in physics are pretty terrible. Such as local and real particles being abstract mathematical objects that can't interact with the universe around them, which is the most commonly used null hypothesis used against the non-local interpretation of the standard model. The other local and real model that physicists use are of particles as very tiny, inert spheres, as if particles are just small marbles moving through the fabric of reality, which is overly simplistic and doesn't work as an explanation for anything. And so in this video, I will describe what I believe to be a much more plausible local and real model of the universe. One where everything is just motion through an infinite amount of space-time and throughout an infinite number of scales, where particles are just dynamic interacting systems of motion. But to get to the point of describing that kind of particle, I'll need to cover the conceptual framework underlying this interpretation first. If the universe has an infinite scale, then it should be thought of as its own dimension, such that the universe has at least 5 dimensions: the 3 dimensions of space, the single dimension of time, and a 5th dimension of scale. This would be to track and compare changes that occur between scales, where the base unit for this dimension is some 3-dimensional volume of space-time. The size of this volume describes the scale that is being observed, where looking at a larger volume corresponds to a larger scale, and a smaller volume corresponds to a smaller scale. This would be like the perspective of the universe centered on this cat from the last video, where a cubic meter could be used to represent the scale of the cat and the environment it resides within, while a cubic light year could be used to represent the scale of our solar system. But changes in scale should be even more significant than just different units of measurement, as scale is more than just a change in size. This is because 2 objects that are separated by scale can exist at the same location in space-time, again like the model of the universe centered on this cat, where it's made of cells that are made of molecules that are made of atoms that are made out of particles. And this cat is on a landmass that is somewhere on Earth in this solar system in the Milky Way that is part of the Laniakea supercluster. All of these objects exist in the same location in the same system, just viewed at different scales. So these quarks are just as much a part of the cat as the cat is a part of the entire observable universe. And so even if the properties of the universe are consistent throughout the scalar dimension, changes in scale should result in seeing different forms of matter and energy existing, at least in part because smaller scale objects collectively add up and create the structures and property of whatever exists at larger scales. Even within the scales of what we are capable of observing, objects don't just build into larger structures with identical properties. Quarks, the cat, and our galaxy all behave very differently from each other. And a lot of this has to do with how the properties seen in the larger scale structures are an emergent phenomenon from the interactions of the smaller scale objects they are made from. As such, changes in scale would be significant enough that it should be thought of as its own unique dimension of the universe. I already mentioned this in previous videos, but an infinite scalar dimension would mean that the constants of the universe would be variables. To be more precise, the universe has fundamental properties, but how those properties are perceived and experienced by an observer would change with scale. Because the properties of the universe as we know them are derived from the small part of the universe that we exist within and are able to observe. Since the smallest things we can measure and manipulate are electromagnetic fields and photons, this puts us in an observational bubble that is restricted in what measurements we can make based on their properties. So the standard model more or less accurately describes the universe, but only from our perspective at our scale using the tools and particles we have access to. Beyond what we can observe would be an even more fundamental set of laws that define how the universe actually works everywhere and at every scale. Like in that thought experiment from the first video, if an observer in a larger scale universe than our own measured the constants of nature, and if they are using proportionally similar units of measurement as us, then they would get very similar values as we do in our scale. However, these values would be absolutely different than what we measure at our own scale, because this observer would have a similar limit in their ability to observe the universe that we do, where they would be restricted to the particles and fields of their scale, which would themselves be larger and more massive than the particles and fields in our universe. And so the constants of nature that the observer measures only describes their scale of their universe. At the extreme edges of that scale, the physics based on these constants will break down to where it looks like there's a ground floor to the universe. But this is only because their understanding of physics is limited to what they can observe, manipulate, and measure. And this would continue for infinitely many scalar universes. A second observer in an even larger scale universe than the first would also have the same observational limits, where they can only manipulate the particles and fields of their scale, which gives them different absolute values for measurements on the universe, which would be larger than ours as well as the first observer's scalar universe. And they too would get a mathematical description of the universe that looks like it contains a ground floor. So the constants of the universe would be variable with scale. They do come from real measurements of the universe, and they accurately relay information about how reality actually works, but only from our perspective and from our scale. The laws of the universe as we know them would not be fundamental. They would be defined as the universe as we see it from our perspective, from the measurements we are able to make at this scale using the tools we have access to. They would be a specialized case of an even more fundamental set of principles and laws for how the universe works throughout the entire scalar dimension. And this has nothing to do with the fact that an observer is taking a measurement. This is just a physical property of an infinite scalar universe. Let's consider a completely empty universe devoid of matter and energy, just empty, motionless space-time in every direction out to infinity. Now let's consider some random scale within this empty void. This reference frame will be some volume of some arbitrary size. We will compare this volume with some smaller and larger scale regions of space. They should all look identical, in that they would obey all the same laws and have the same energy potential throughout their volume. However, while the laws of the universe don't change, there are still differences in scale. If each scalar region were to get a proportionally sized wave, then these would each represent different energy levels, because it would take relatively more energy and time to create a wave throughout some arbitrary larger scale than it would to create an equivalently proportioned wave at some smaller scale. As the volume of spacetime being considered changes, the energy required to create an equivalently sized wave and the energy that would exist within them relative to each other would change. And with an infinite scalar dimension, there could be infinitely many larger and smaller scale regions, each with their own proportionally sized waves. There wouldn't be an absolute large or small. Size would be relative to what reference frame is being used to make comparisons. So there are laws for how the universe behaves, but we are only ever capable of measuring and observing a small part of nature. These measurements accurately describe reality, but only from our perspective, at our scale, with the tools we have available to us, which may partially explain why physics equations go to infinity at the extremes of the scales we can observe, because the laws were fixed to our perspective. Time is the progression of events, where things normally go from one moment to the next in a forward progression of actions, or forward in time. It is measured by the intervals of some process that repeats or can be repeated. The Earth continuously rotates around its axis at more or less a steady rate, so each 360-degree rotation is a unit of measurement we call a day. Just about any repeating process can be used to measure time, such as the swinging of a pendulum, the falling of a quantity of sand, or even the interval it takes for a certain number of fluctuations to occur at the quantum scale, like the current definition of a second. But that's just how time is measured. That doesn't explain what time is. In this interpretation, the dimension of time tracks the motion of things. Think of it this way. The three dimensions of space contain the axes of up-down, left-right, and forward-back, which keep track of where something is in a single moment in time. As in, A thing, like this cat, exists at this location right now. But in order to discuss that cat moving, such as walking from that location to somewhere else, would involve the dimension of time. This is usually represented with a space-time diagram where one axis represents space in only one dimension, while the other axis represents the dimension of time. If this cat walks from location A to location B, it's obviously moving through space, but it would also be moving through time. The intervals it took to move that distance is the measurement of time. The angle that the cat travels on this graph represents its speed. By convention, a 45-degree angle is used to denote the speed of causality. But even if this cat were to lay completely motionless, it would still be traveling through the dimension of time. It would just be doing so at that one location. This is because time is always progressing for all things in the universe. Everything that this cat is made of, the atoms and particles, and everything else at potentially infinitely many smaller scales, would still need to be fluctuating in order for the cat to continue to exist. The properties of physical matter come from the bonds and interactions of their constituent parts. So if all the components of the cat stopped moving, they wouldn't be able to interact to create the structural bonds that form larger structures. The bonds between atoms and particles wouldn't form, and without this motion and interaction, the cat would just fade out of existence. Which means that even when laying perfectly still, this cat would still be moving through time, because their constituent particles and components would be in constant motion. Otherwise, the cat couldn't exist. This is how time is related to motion. It defines, comes about, and measures the motion that exists within the universe. Under this interpretation, the flow of time should be relative between different scalar locations. We should expect time to be flowing relatively slower at increasingly larger scales, and flowing faster at increasingly smaller scales. At least it would be if the universe had an infinite scalar dimension. For a start, things that exist at larger scales would have more mass than smaller scale objects by definition. This would mean that they would require more energy to move. So relatively larger scales would require relatively more energy to move than a smaller scale. Although there is a more physical reason for time to vary, because scale isn't just about variations in size, it's about how different structures can exist at the same location, just separated by scale, and how smaller scale objects can interact to form larger scale structures. The creation of large-scale structures doesn't come from the existence of matter alone. It's the movement and interactions between the constituent parts that creates the structures and properties at larger scales. It's like a compound gear setup, where several smaller gears turn a series of increasingly larger gears. It requires that the smaller ones rotate more to cause movement in subsequent larger gears. And each set of subsequently larger gears require even more movement from the smaller ones to move. Likewise, it should take more movement from smaller scale objects to cause any movement in larger scale structures they create. And it would take some noticeable amount of movement at this larger scale to create even larger scale structures, which could go on indefinitely. For every tick of some unit of time at some arbitrarily larger scale, relatively greater amounts of movement would have to take place at potentially infinitely smaller scales to create that structure and its motion. Otherwise, that small moment in time couldn't have existed. Which means that any amount of time at any scale is created from all the movement that exists from the smaller scale objects they are made from. This would be true even if scalar universes are separated where structure formation stops at some larger scale. Because our universe would be affecting the boundaries of any potentially larger scale universe, as the shape and extent of the emptiness between our universes would be dictated by the matter and energy that exist at our scale. Since the change in scale is geometric, changes within it should be altered exponentially. So even if structure formation stops in our universe, then at some even larger scale than that, the impact of our matter and energy would be indistinguishable from nothingness. After this point, any increase in scale doesn't significantly change our impact on the universe, which should allow for something else to exist, like the quantum fluctuations of a larger scale universe, which is just a slight variation on that larger scale universe from that thought experiment of the observer. So even though we would be separated, this larger scale universe would still be more massive than ours, and by definition would require more energy to move. So even with a void between scalar universes, time should still be experienced differently between two scalar observers. which is one of the biggest implications of an infinite scale, that smaller scales experience more time relative to larger scales. There's one problem that all local and real models have. What exactly is everything made out of then? The standard model has its own answer, that at the smallest possible scale, there exist quantum fields that create particles and mediate interactions. But this can't be true for local and real models, because quantum fields can only exist if there's a ground level to the universe. So particles would need to be made of something else in order to have some physical and tangible presence. But what that could be has long been a problem for locality. Different ideas have been proposed throughout the years for extra substances that exist in the universe. Most famous is the luminiferous aether. But so far, all of these ideas have failed, either due to a lack of evidence or from experiments proving them wrong. To date, there is no evidence for the existence of some unknown substance in the universe, which means there's nothing for real particles to be made from. So instead of trying to invent something new with imagined properties that we can't detect, I'm going to propose going with the most straightforward answer that involves very little new physics. That everything is just made from space-time, that's stretching and deforming and interacting with itself. There's at least some evidence that space-time exists and has properties. Or more accurately, it's at least possible that space-time exists, because there's still some debate among physicists about whether or not space-time is actually real. That debate largely comes down to the fact that general relativity breaks down at the quantum scale. Since quantum physicists tend to believe that they are studying the bottom floor of the universe, where all the properties of reality emerge, some physicists view this as evidence that spacetime is just an emergent phenomenon of quantum fields. But I would argue that general relativity breaks down simply because we are in an observational bubble and the constants are variables. They describe how phenomena in the universe work only from our scalar perspective. It should be expected, then, that the equations of general relativity break down when asked to describe the extreme edges of the scale that we can observe. This would just be a problem with our scalar perspective being baked into the equations itself, and not a property of spacetime. So if spacetime does physically exist, then it appears to have the properties that it can move and be manipulated. From the expansion of the universe, we know that spacetime can expand outward. And from the warping of spacetime around gravitationally dense objects like stars and black holes, we know that spacetime can warp inward. And gravitational waves have been measured, demonstrating that spacetime can wave and flow. So spacetime can move and be manipulated, at least by expanding and contracting, and through fluctuations and waves. If we add an infinite scalar dimension, then we have a thing that exists everywhere, and at infinite scales, that can move and be deformed. This is, I would argue, at least a decent start in the search for a substance of everything. Everything then would just be fluctuations of spacetime. The fundamental properties of the universe would be those of spacetime, and how it moves, fluctuates, interacts, and changes properties at varying scales. As for what spacetime is, I don't know. At the very least, I would say that it has the properties of existing, of being able to move and warp, and of being infinite, which tracks onto the dimensions of space, time, and scale, respectively. So I guess I'm saying that spacetime would be those properties realized. That's the idea I'm proposing anyway. A local and real universe where all interactions are mediated by the motion, fluctuations, and distortions within an infinite expanse of spacetime with an infinite scalar dimension. An infinite scalar dimension may provide a possible answer for how the universe came into existence, or how the universe goes from being filled with vast nothingness to containing all the matter and energy and everything we see around us. Because what do we have when we combine 3 dimensions of space, 1 dimension of time, and 1 dimension of scale? We have a gradient. I mean, of course there's the gradient of scale, where different scalar sections will contain different volumes of space-time. But more importantly, there's the gradient of time, where more time intervals pass in smaller scale regions than in larger scale regions. And gradients in nature usually imply movement. This could be what caused the first fluctuations in the universe. Space-time exists, but at first there's nothing. No forces or initial interactions to create matter or complexity. Just smaller scales of space experiencing more time than the larger scales they are part of. Because time is defined in this interpretation as tracking motion. So for something to experience more time, it would also mean that it's experiencing more potential for motion. And each section of space would be made of infinitely many smaller scale subregions, each of which is experiencing more time than the scale above it. And each section of space would be part of infinitely many larger scale regions, each experiencing less time than the scale below it. If nothing else, this should provide a mechanism where fluctuations could occur in spacetime due to a gradient of time, where smaller scale fluctuations interact and build into larger scale fluctuations, which themselves interact and build into larger scale fluctuations, and so on throughout infinite dimensions and scale. The creation of any kind of disturbance would start to fill the universe with something, movement. At least it should according to this framework. How such fluctuations could give rise to universes like our own is beyond this series. It would take a more substantial model to give any definitive answer. But this is at least an explanation for how the universe could go from containing nothing to being filled with matter just from the presence of the 5 dimensions of reality, where we should expect a gradient of time, which could possibly result in the creation of motion, which may lead to the creation of all the stuff in the universe. One important note though, when talking about things starting, it shouldn't be taken as there being an actual start date for the universe. There shouldn't be a singular beginning to matter and energy, because within an infinite scale, it should be possible to always find a place in the universe that's older than another location. Say you could find a spot in the infinite 3 dimensions of space that you could call the oldest spot of that scalar plane. If you then go down in scale at that location, then you would be passing through regions of space that are older in time relative to the larger scale, because smaller scales experience more time relative to larger scales. Which means that even if you couldn't find an older location in space, you could always travel through the scalar dimension to find something that is even older. As in, there is no beginning of time or oldest point in the universe. There is no universal reference point. Everything is relative. With all that out of the way, I can finally begin to answer what particles are in this interpretation, which would be stable dynamic interacting systems of fluctuating spacetime. Because in this interpretation, matter isn't a solid object, rather it would be made of the interactions that happen across empty space between their constituent parts. And those constituent parts would also be mostly empty space, made of the interactions between their component parts. And this could possibly go on through infinite scales, because matter is mostly just empty space. Let's start by discussing mass, which is the energy contained within a structure or region of space. The fundamental particles that make up matter, the electron and the up and down quarks, have an intrinsic mass from the act of simply existing, what is called their rest mass. This is where the mass in regular matter originates. However, the total mass of an atom is much larger than the combined rest mass of all the quarks and electrons that it contains. The vast majority of an atom's mass actually comes from the strong force interactions between quarks that creates protons and neutrons. So most of the mass of an atom doesn't come from the existence of its constituent particles. It comes from how those parts interact with each other. It should be noted that mass is not created from all interactions. It's mostly just the strong force between quarks. In fact, the binding interactions of atoms and molecules generally reduces their overall mass, as it takes energy to create these bonds. So while interactions between different objects can create different structures, it doesn't always create mass. This is a start to what I believe matter could be in a local and real universe. Objects and the interactions between them at different scales. Together they create new structures at larger scales which can themselves interact to form larger scale structures, where the basic units of matter in this interpretation are structures, objects, and interactions. Basically, some number of objects interact to form some larger scale structure. Some number of these structures could also interact to form an even larger scale superstructure. But also, these objects would be made of the interactions between some number of objects. And each of these objects could themselves be made of the interactions of some number of even smaller scale objects. And this could be repeated through potentially infinitely many scales. This would be the general pattern in an infinite universe, the fractal equation if you want, where spacetime fluctuations at some arbitrary scale and below can interact to form some larger scale structures, and so on for possibly infinite iterations. It's not self-repeating at every scale, it's just an iterative process of interactions over time. But what I am calling structures aren't actually solid masses. They are an emergent product of the fluctuations and dynamic systems they are made from, as matter would mostly just be empty space. Which is an observation that has already been made about our universe. There are great distances between galaxies, star systems, and even stars and planets. Most of the cosmos is just empty space. But this is true of the small scale as well. If you take this cat and look to see what it is made from, it turns out to be mostly empty space. The distances between molecules and atoms is just as vast as on the cosmic scale. So this cat is mostly empty space, only gaining structure and properties due to the interaction of the objects it's made from. The same as with this galaxy, which is mostly empty space, only gaining structure and properties from the interactions of the objects it's made from. Matter is mostly empty space. It's the interactions between objects that create structure. And in this interpretation, these interactions would all be fluctuations in space-time. And this is how particles and everything else in existence could be dynamic interacting systems of fluctuating space-time, where the most fundamental force in nature would be motion. Which means that matter is just an emergent phenomenon from the movement of smaller scale things. Although those smaller scale things are just made of motion and interaction as well. It's just interaction and motion all the way down. In this interpretation, this would all be movement in space-time. So fluctuations within space-time can combine to create some larger scale motion. These can interact to form larger scale structures. These structures would then be dynamic interacting systems of fluctuating space-time. This could still work even if there really is a point in scale where structure formation stops. Because all matter would be created from interactions and motion in space-time. They should only need some fluctuations that interact at some smaller scales in order to be created. And there's some evidence of something like this with quantum fluctuations, a background vibration of space-time at the smallest scales. So our universe could end at some scale, and above that would be emptiness. But at some even larger scale, there could be some random fluctuations. These would accumulate at larger scales into more fluctuations, until this builds into enough stable movement to support the base object for a dynamic interacting system of space-time, or another particle. So particles in this interpretation are emergent phenomenon caused by the motion and interaction of space-time over infinite scales. There are no truly solid objects. Instead, structures are just the result of the stable and dynamic motion and interaction that's happening over a potentially infinite number of smaller scales. It's like that cat on the space-time grid. In order for this cat to truly stop moving in time, its atoms and all the particles that create those atoms would need to stop moving. But without motion within these particles, there are no interactions, which means there's no structure. And so, if this cat stopped moving in time, it means it has stopped existing entirely. I'd like to wrap up this section with just a few points. First, there wouldn't be clearly defined scales to the universe. Not just in the fact that everything is relative, but that the influence of a certain type of structure can spread out among a range of scales. Take the electron, for example, which, if it has a size, should exist somewhere near the scales of a quark or below. However, the influence of electrons extends to scales up to the creation of atoms and molecules and beyond, even influencing the properties of large-scale matter. Which means that things don't exist at one scale, they exist and exert influence within a range of scalar dimensions. Second, there are more complex interactions than just small-scale stuff make big-scale stuff, as interactions can also move both up and down the scalar dimension. Take life as an example. Obviously, life is made from the interactions of atoms and molecules, which are smaller-scale objects. However, life can't easily form and flourish without even larger-scale objects like planets and stars existing to create the room and resources necessary to carry out the chemical processes of life. Which means that life can be seen as coming from the interactions of both larger and smaller-scale structures and interactions. But more than that, life is an example of a microchain structure. Atoms form molecules that form into cells and tissues that form into living organisms. But all the life that exists on Earth is just a small part of the chemical makeup of the planet we inhabit. And whether a planet forms life or not has little effect on how it interacts with the rest of the universe. So life is a smaller sub-chain of interactions contained within the larger chain of interactions of the universe. If everything is just movement within space-time, then fields and waves would most likely just be fluctuations and directional flow of space-time, at least under this interpretation. This would mean that the electromagnetic force, the strong force, and the weak force would all be created and mediated by the movement of space-time. I will get back to this in a later video when I discuss quantum mechanics directly. but the general idea is that everything is moving spacetime, including fields and waves. I think that a reasonably good model for a local and real particle already exists. In the standard model, the best description of spin isn't of particles spinning, but rather of particles as spinners. These are point-like objects that possess invisible attachments to the universe around them. It looks like these representations here, where there's a singular point which represents where a particle would be located, that is attached to the rest of the universe at every point on its surface. The number of attachments shown in these diagrams is arbitrary, as spinners could have infinitely many. Regardless of their number, a spinner can freely rotate without getting these attachments entangled with one another. But due to how these connections are arranged, it's possible that a single full rotation, or 360-degree turn, will not bring a spinner back to its original state. Instead, these attachments would be twisted from their original positions. In order to get back to its original configuration can take 2 or more rotations. If it takes 2 rotations, or a 720-degree turn, then the spinner has a spin of 1/2. This describes particles of mass like quarks and electrons. And I think spinners make a good visual representation for the real and local particles that I am proposing, just so long as we make a few assumptions about what we are looking at. If we assume that everything is just spacetime, then this diagram becomes a dense point of fluctuating spacetime that has attachments to the rest of spacetime, where these attachments are the pull and flow of spacetime in, out, and around the particle. It's not a perfect representation, as it represents the particle as being point-like instead of taking up some volume, but it's close enough for this local and real interpretation. So a particle exists at one location, but its influence on space is exerted over some distance beyond that. As the particle moves and its internal components spin, these spacetime distortions move and spin with them. But the idea of this interpretation is that objects are made of potentially infinitely many smaller scale objects, and are also a part of possibly infinitely many larger scale structures. So under these assumptions, a particle wouldn't be a solid object. Instead, it would be made of the interactions between some number of smaller objects, which could be modeled as spinners as well. It would be the interactions between these different objects that create the original spinner structure in the particle. And this could go on through smaller scales, where each of these component objects would also be made of the interactions between smaller spinner-like objects, where we are never able to truly find a solid physical structure in the universe. Everything is mostly just empty space. Except that fluctuations and interactions that exist within this empty space build structures. So really, particles, and all other structures with mass, are emergent phenomenon from the fluctuations and interactions that exist within this empty space, which is what local and real particles could be: dynamic interacting systems of moving spacetime across an infinite scalar dimension. And to wrap up, in the standard model, the property of spin can't just be the particle physically spinning, as an electron would need to be spinning at least 1,000,000 times faster than the speed of light. But this comes from viewing particles as inert spheres in a universe with a bottom floor to reality. With an infinite scale, however, a smaller scale object could be experiencing more time relative to a larger structure. So it could be possible that an electron goes through more time than us, which might affect how we observe its properties and behavior. And in the model I am proposing, spin doesn't just come from particles physically spinning either. It also comes from the movement and interactions of the objects that a particle is made from. So it's not necessary that an electron needs to be spinning faster than the speed of light, only that the energy from the motion of the electron and the interactions and movement of its component parts equals the energy of its field strength. There's a relationship between mass and energy that's fairly well established. In this interpretation, I would add that they are both related to motion. Let's consider a particle inside of a region of space. It has some rest mass from existing. This mass is also just energy. But under this interpretation, mass is the movement of spacetime pulled in by the interactions and motion of smaller component objects. And the mass of those objects is caused by spacetime being pulled in by the interactions and motion of even smaller components, and then by even smaller objects, and so on into possibly infinite iterations. The mass of this particle, then, is the sum total amount of energy contained in this region of space, which all comes from the motion of spacetime. But each region of space can only hold so much energy. There are physical limitations to how much motion is possible at any particular scale. These limitations can be seen in physical laws like the speed of causality, which states that the more mass something has, the more energy it will take to make it accelerate. If something has any mass at all, like this particle, then it would take an infinite amount of energy to accelerate that object to the speed of light. The ability for this particle to accelerate depends on its mass. The more mass it has, the less easily it can move. Under this interpretation, mass would come from the dynamic interacting movement of smaller scale objects. It would just be motion. So the more mass something has, the more motion is intrinsically present in a region of space, meaning that the universe has some limit to the amount of motion possible in any volume of space-time. Accelerating the particle, then, means putting more energy, more motion, into this region of space to increase its velocity. If the particle is massless, like a photon, then all the energy in this region is being put into velocity. Nothing is mass energy, meaning it travels at the speed of causality, which may offer an explanation for time dilation, where it's about the limits to how much motion is possible in a region of space, where structures that contain mass, as well as the objects that they are made from, would slow down moving as the entire unit accelerates, as more energy goes towards velocity. To explain, a hypothetical particle starts out by traveling at some speed. This is its reference frame. It already has some amount of velocity energy, and it and the objects it's made of are able to move at a certain rate at this speed. If this particle is accelerated, it means that more energy in this region is devoted to velocity. And it means that the particle and its component parts would now have to put more energy into moving in some direction at even greater speeds. So less energy is available per increment of time to be used for the movement and interactions that create and maintain the particle's existence. Therefore, the particle experiences less time as less motion takes place in its overall structure, meaning that time dilation could come from the physical limits for motion in spacetime. But what about electromagnetic waves and photons, which are supposedly things made of only velocity energy, just fluctuations in spacetime that are devoid of mass? Well, electromagnetic waves would just be that. Fluctuations in spacetime at the size and scale where they travel at the speed of causality relative to us. They wouldn't be the smallest fluctuations measurable because they're the bottom of the universe, but because they're the smallest things we can measure. But in this model, it's possible for photons to be particles, or a dynamic interacting system of spacetime. This is because changes in scale represent a geometric change in volume, meaning changes in scale are exponential. So at some smaller scale relative to us is a point where the mass energy of an object would look equivalent to nothing. So perhaps a photon has a mass that is so small relative to us that it's indistinguishable from being nothing. However, they are still capable of producing fluctuations in spacetime with the energy of electromagnetic waves, meaning we can see the fluctuations a photon produces, but not the particle itself. Except, of course, for when it's measured. Then it's always measured as a particle. This should be possible because all frames of reference should be valid. So we could ask what the universe would look like at the scale of a photon, assuming that photons are particles. What if the observer from the thought experiment were to decrease in scale to this size? Well, for one, any photon they looked at wouldn't appear to be traveling at the speed of causality to the observer anymore, because relative to them, the photon would be of some massive size. From this perspective, it would take an infinite amount of energy to accelerate this photon to the speed of causality. And if the observer were at all able to see us at our scale, then we would appear to be barely moving relative to them and the photon. And at some smaller scale to the observer would be a level where some particle or fluctuation would be moving at the speed of light relative to them. And so photons wouldn't intrinsically travel at the speed of causality. They only do so when viewed from the scalar perspective that we have on Earth, where they appear to be so small relative to us. So mass, energy, and motion are all relative to observers at different scales, because all frames of reference would be valid in an infinite scalar universe, and all things would be motion in spacetime. It's unknown how our universe came into existence. What evidence we have points toward everything starting out as a single point, a singularity, that expanded for some reason, creating the universe we live in today. While a lot is known about what happened after the Big Bang epoch, anything about its cause or extent is purely speculative. Even so, I'd like to discuss the four main possibilities that present themselves with this interpretation. These break down on two assumptions about the universe. Was the Big Bang a universal or local event? And does matter and energy exist everywhere at almost every scale, or do large voids exist between where matter is present? Usually in physics, the Big Bang will be talked about as an event that happened everywhere out to infinity, a universal event. The expansion of the universe occurred at every point in space at the same time, so matter and energy are more or less evenly distributed in every direction. However, there's also the possibility that the Big Bang was a local event that created a finite amount of matter and energy. So the observable universe would just be a small part of some larger bubble universe, and our bubble universe would just be one among a sea of potentially infinitely many other bubble universes, all created from their own individual Big Bang singularities, and that all exist within the greater whole of reality. This would be a multiverse, but not of other worlds existing in parallel dimensions stacked on top of one another. This is a multiverse where other worlds exist separated by physical distance and scale. And the second axis relates to whether structure formation continues to happen throughout the scalar dimension. As in, does matter and energy exist throughout the scalar dimension, or can large voids exist between regions with matter? Because it's possible for galaxies to stop forming larger structures at some point, and for our universe to be part of some even larger scale universe. So structure formation on our universe stops, but above that, at some even greater scale, matter and energy could once again form, but it would be separated from our own world. So let's start with the assumption that the Big Bang was universal and matter and energy exist in all directions and scales out to infinity, where the expansion of the universe happened and continues to happen everywhere all at once. Since in this interpretation, all things may have come about from the gradient of space-time and scale, the Big Bang would need to be explained as a result of this gradient. So, maybe, the gradient in time could have caused movement from smaller scale regions upwards towards larger scales, thus creating inflation. Of course, that's just speculation. However it happened, the universe expands everywhere and at all scales, creating a constant chain of interactions that create matter everywhere at every scale. A related idea is that the Big Bang was universal, that it happened everywhere, but there are voids between where different scalar universes of matter and energy could exist. This is a lot like Roger Penrose's cyclic cosmology model, only where different universes are separated just by scale and not time. The general idea would be that at different intervals in scale, fluctuations are created that eventually expand into universes. So infinitely expansive universes are created by each Big Bang, but they are separated by scale. And because changes in scale are geometric, each scalar universe has little to no effect on each other. In this way, multiple scalar universes can coexist at the same time, but they are separate and do not build into each other. Then there's the multiverse models, starting with the one where structures continue to form throughout the scalar dimension. Because even if the bubble universes themselves didn't directly interact, they could still influence and shape the scales above them. Because at a minimum, these bubble universes would either be in a state of a singularity, an expanding universe, or somewhere in between these two states. With infinitely many universes popping into and out of existence, it would resemble what quantum fluctuations look like to us. These could then shape the scales above them. Anyway, to explain this with the space-time and scale gradient, I suppose this would mean that matter and energy formation comes from local interactions. Singularities form due to the iterative interactions between different regions of fluctuating space-time, which over time forms localized dense regions that can eventually expand, creating matter and energy. I would suppose that a big difference between whether a multiverse will have an infinite chain of structure formation, or if it will be broken up by large voids, is whether fluctuations in space-time will occur or can occur. In the first case, due to the space-time and scale gradient, motion will occur, and matter and energy forms practically everywhere at all scales. In the second case, space-time fluctuations can occur, but won't without meeting certain requirements beforehand. It's only under the right conditions that matter and energy can not only form, but also maintain structure. So the universe could be filled with clumps of matter that are separated by large voids of mostly nothingness. Again, this is all highly speculative, and without a more robust model, there isn't a lot more to say. But in general, these appear to be the most likely explanations for the Big Bang under this interpretation. Personally, I like a multiverse with matter and energy distributed throughout the infinite cosmos, where space-time fluctuations will just happen over time, It's the perspective from which I have created this series, because it would appear to match what we see happening through the scales that we can observe, where our observable universe would just be a bubble universe inside of some large structure, which itself is just a part of some larger structure, and so on into infinity. But that is just pure speculation on my part. This is about as far as I got in trying to create an explanation for how the universe works by simply thinking about the nature of an infinite scalar dimension. As I said before, I can't say that this actually describes how nature really functions. It would take substantially more work to say anything definitive. Even if the universe is local and real, it could work in other ways beyond what is imagined in this series. But if nothing else, I thought it was worthwhile to share because so few people bother to take these concepts seriously. Especially not a 5-dimensional universe where there's an infinite scale. And I think this is a much more plausible framework than any of the local and real hypotheses currently used by physicists. Because these particles are actually local and real, not some abstract mathematical concept or an impossibly motionless sphere. And I'd like to demonstrate the strengths of this idea by discussing what the interpretation could mean for the nature of dark matter in the next video, which would be that dark matter is just more fluctuations in space-time. On the galactic scale, it would come from the movement and interactions between star systems and black holes. I hope that you will continue to watch this discussion of an alternative interpretation of physics.